Good evening, ladies and gentlemen. Welcome to the seventh series of Geosynthetic webinar under the theme Failure Investigation of a Geosynthetic Rainfall Soil Slope Subject to Rainfall. This event is brought to you by International Geosynthetic Society, Chapter Indonesia, which also known as INA-IGS. My name is Stephanie Bigel, and it's a pleasure to be the master of ceremony of this event. Before we start, please allow me to read the rundown of our event this evening. First, I will be reading the rule of the webinar. Second, there will be an opening remarks by the member of INA-IGS, Mr. Insinyur Doyolujeng Dwiarso MM. After that, the event will be guided by Mr. David Saputra MM as a moderator to start the presentation of Professor Kuo Shin Yang, PhD. The event will then continue with a Q&A session. After the Q&A session, we'll be doing a quiz with a very interesting prize for the winner. So we would like to ask you to stay with us until the end of the event. At the end of the event, we'll also give you the access to the e-certificate and the soft copy of the presentation. That's all for the rundown of today's webinar. Ladies and gentlemen, for your own convenience, please put attention to the following rules and notice. First, you can submit your question for the speaker through the Q&A feature that's located at the bottom of the screen, and the question should be in English. You can submit your question before, during, and after the presentation of the speaker. Second, we expect you to stay until the end of the webinar to get the information that you need regarding e-certificate and also the soft copy of the presentation from the speaker. Third, this event is also live streamed on INA-IGS YouTube channel, or you can directly go to the link s.id/INA-IGS07YT. Fourth, if there's any technical difficulties, please contact Mr. Sandy at the number that has been shown on the screen. That's all for the rules and notice. Without any further ado, I would like to invite Mr. Insinyur Doyolujeng Dwiarso MM as the member of INA-IGS to give his opening remarks. To Mr. Doyolujeng Dwiarso, the time is yours.
Good evening for the participants from Indonesia, or good afternoon, or even good morning for the participants from other time regions. Distinguished participants, ladies and gentlemen, my dear friend of science, technology, and innovation. On behalf of the Indonesian chapter of the International Geosynthetic Society, INA-IGS, I am pleased to welcome you to the 7th webinar of INA-IGS Geosynthetic. This webinar is one of our programs in hope to distribute valuable knowledge from respectable speakers to our members and also, of course, to all of these webinar participants. I am very delighted to have invited our very insightful speaker who will talk about the topic of the webinar, which is failure investigation of geosynthetic reinforced soil slope subject to rainfall. This respectable speaker is Professor Kuo Shin Yang, PhD from the National Taiwan University. Professor Kuo Shin Yang, PhD, as member of INA-IGS, I would like to welcome you to this webinar and also to express my gratitude for sharing your knowledge and insight regarding the topic with our participants today. And I also welcome you once again, participants of today's webinar. Thank you for your participating, and I hope you can gain valuable knowledge from today's event. I also would like to thank all committee for your contribution in holding this webinar. Together, let us accelerate the exchange of ideas and scaling up of good practices. Please and enjoy the 7th webinar of INA-IGS Geosynthetic. Thank you.
Thank you, Mr. Doyolujeng Dwiarso, for your kind remarks. Ladies and gentlemen, we would like to remind you that you can start submit your question from now by using the Q&A feature. We I also want to remind you to stay with us until the end of the event for the quiz session and to get the information regarding the e-certificate. Now, this webinar will be guided by Mr. David Saputra MM as the moderator. Please welcome Mr. David Saputra. The time is yours.
All right. Thank you, Stephanie. Okay, now I have the honor to introduce our speaker for today. I hope I can pronounce his name properly in Mandarin. This is our speaker will be Professor Yang Guoxin. He is currently a professor and associate chair of Department of Civil Engineering at the National Taiwan University. Now, I've seen his biography, and yes, you can also see it on your screen there. But what you see on the screen there is only a little bit of what of his achievements. He has done so many. He has made so many achievements. He has authored many publications and received many awards for them as well. Now, he's got a very long biography, but it's a shame I don't think I have the time to be reading all of it for you. So I'll just cut it short so we can quickly get into the materials and let Professor Yang take over. Just a little bit more though. He has conducted many research and projects on the analysis, design, and case study of geosynthetic reinforced soil, or GRS, structures using both numerical and physical modeling. Now, the research results are then applied to prevent and mitigate the natural disaster-induced damage or collapse of these structures, and to ultimately establish sustainable and safe infrastructures. Now, recently, Professor Yang is dedicated to investigating the performance of GRS structures with marginal backfills subjected to rainfall as a common and significant problem for the application of GRS structures in Taiwan and Southeast Asian countries located in the tropical areas. That's us. The good thing is, based on the results and findings from the research, methods for backfill selection, stability evaluation, as well as improved design recommendations are proposed to benefit the practical designs of GRS structures against heavy rainfall. So this is exciting. I won't take too much of your time anymore. So let's welcome Professor Yang.
Okay, thank you. Thank you for the very kind introduction. Should I share my screen? Yes. Okay, good evening, all the participants. I wonder, can you hear me?
Yes, we can hear you.
Okay, thank you for to participate today's webinar. And I see many in the participant list, I see many good friends of mine, and also the former students of my students. And thank you for all your participations. Today I'm gonna tell you, share you one story about the failure of the geosynthetic reinforced soil slope, and due to the heavy rainfall. And from today's talk, I'm not only to tell you the failure story, but I want to tell you what is the reasons and how to improve that. What is the lesson that we learned from these failure cases? Okay, I think David already gave a very detailed introduction to me. My research work related to geosynthetic was recognized, and I was received the INA-IGS Member Award in 2014. And recently, last year, one of my papers, which I'm gonna present today, received the second best paper award from the Geosynthetic International Journal. I was also served as an editorial board members in the geotextile and geomembranes journals. Okay, before that, I would like to share you some photo of our campus. I really want to invite you all to go to NTU, and I'm happy to show you around. This is the night view of NTU library, and you can see the Taipei 101 at the background. This is the library, and this is the Royal Plum Boulevard. But ride a bicycle in the summer is very hot. And this is the lake in NTU. Okay, this is the presentation outline. I will introduce the background of these case studies. And then I will talk about what is in the practical engineering using the conventional limit equilibrium analysis. And what is the limitation for analyze the slope stability when there's a rainfall problems. I will also introduce a more sophisticated model. It's called hydromechanical models and the validation with the value case studies. And after that, I would like to propose some assessment for remedial measures to improve the stabilities. And finally, I like to talk about, based on the lessons we learned from these studies, what is the design and construction considerations we can learn from this talk. Okay, so that's the background. Kerr Tazagi, the father of the soil mechanics, said that a well-documented case history is valuable and should be emphasized. And we are doing that today. The case I'm gonna introduce you today is a multi-tier reinforced slope. And it's what constructed in here to provide the traffic access to the uphill, the landfill in the uphill in Taiwan around 2010. In addition, the GRS slope was also used to stabilize the original rock slope behind the GRS wall. This multi-tier slope total is 26 meters high and has 4 tiers. The backfill is used locally available soils. I think this is a typical tradition in Taiwan. I will tell you why. The reinforcement is the geogrid, and the facing element is the sandbag and then geogrid rubber round in both sides of the GRS slope. And they do design for drainage. There's a geocomposite as a back drain, and also there's a 150 millimeters drainage pipe at the 2 meter spacings was installed at the bottom of each tier. And the original slope consisting of the weathered sandstone and shale. So that's the problems. The backfill material is the low plasticity sandy silt, classified as a CLML. And there's over 60% of fines, and which is contrary to the backfill recommendation in the design guideline. The backfill material is just taken from the local, and this is residual soil from weathered sandstone and shale. And we identify the soil shear strength can be significantly reduced when the soil becomes wet. I think the main reason is because use the local available soil is because we want to try to reduce the cost and the environmental impact associated with you have to transportation the good quality backfill to construction site, and then you have to dispose of the poor quality backfill in the situ. In addition, in Taiwan, we have environmental regulations. That means when you construct a project in slope, the excavation and the backfill, the amount of the soil should be balanced. So usually people won't like to select the backfill. They will use whatever they can find in the field. Even this contains high % of fines. Okay, but we learn from the Dr. Corners. They do the statistic data of the GRS structures, and they found the main reason to cause the failure is they are around 76% using the marginal backfills. 60% the failure are caused by the waters, no matter it's internal or external waters. 80% have poor compactions, and around 90% fail less than 4 years. And if you do the math, this is add up larger than 100. That means most of the time the failure consisting 2 or more reasons. And later I can show you these 4 problems all happens in the presented case study. So this is the design guideline suggests in ASHTO or FHWA. And they say for the backfill requirement, for the wall and the slope, the fines content pass the number 200 sieve. For wall, should less than 15%. And for slope, should less than 50%. And this also have the requirement for plasticity index less than 6 and 20s. If I plug in this grain size distribution curve, in these regions, this is called compliant soils. The soil is acceptable. But if the grain size distribution fall inside these regions, and we call this is the marginal soil, and this is not acceptable. Okay, these walls are built, sorry, this slope was built in 2010. However, you can see after seasons of typhoon and heavy rainfall, local people found there's a tension crack develop, and then that's a settlement at the top of the slope. And then they initiate the slope monitoring for the deformations. During the monitoring, they found the slope deformation will reach to 140 and 80 centimeters from June to December of the 2012. That means 2 years later. The slope was repaired because there's a very big settlement, over 1 meter. The slope was repaired by backfilling the soil to the design elevations. And although it was repaired, the slope still fell after 2 sequential typhoons and in September, after 1 year. The first question come to my mind is whether this slope deformations is associated with heavy rainfall or caused by soil creep deformations. And this question can be answered by looking at the settlement versus rainfall data. And you can see during the summer typhoon seasons, there are many rainfall and cause a significant settlement. But during the winter dry seasons, there's not too much rainfall, so the deformation seems to stop. So the concern that the slope settlement due to the creep deformation can be excluded. So we can conclude that the settlement was directly caused by the heavy rainfall. This shows the rainfall data of the Typhoon Changmi and the Typhoon Kangri, which brought over 600 millimeters of precipitations in these areas, and the slope failures in the end of the August. I want to show you some photos. This is at the beginning. You are looking at the top, the crest of the slope, and that's deformations develop the tension crack and the settlement. And this is the settlement increase a lot and become over than 1 meter. So people tend to repair this slope by just simply backfill the slope to the original height. But they don't know they do that while adding additional surcharge to the top of the slope. Okay, and so, and finally, the whole slope was failed. You can see there's a close view of the slope toe after failures. You can see the first tier, the bottom tier kick out, like a sliding forward. But I would like to have your attention on the water seepage and the water ponding on these photos. This suggesting the soil have very high moisture content, at least at the bottom tiers. And this moisture content likely reach to fully saturations. You can see even in the sunny day, several days after failure, the water still seeping out from the backfills. Okay, this is another view for the first bottom tier. This slide shows the topographic and the inference areas of the failure slope. And the total width of the failure area range from 30 meters to 50 meters. The failure surface is a compound failure surface. So we say this is a compound failure mode, meaning that the failure surface partially cuts through the reinforced zone at the bottom tier and partially cuts through the original back rock slopes. The drainage, they do installation of the geocomposite as a back drain, and this is to collecting the water can potentially seeping out of the original rock slope surface. And then they also input this transverse 100 millimeters transverse drainage pipe installed at the 2 meter spacings. And this is try to convey the water from the back to the front of the slope. And there's also a 600 millimeter diameters vertical internal drainage pipe. And this was close to the wall slope facings to collect water and guide water out into the drainage ditch. So just let me remind you, they put the geocomposite in here, and that's a transverse pipe. And we also have the vertical drainage pipe and guide the water to the drainage ditch. But the problem is, although the installation of the drainage is done, but it's suspected that the drainage system may malfunctions. You can see actually the interface, the connections, these drainage joints are poorly connected during the constructions. No matter it's between the geocomposite and transverse pipe or the drainage ditch and vertical pipe. This is just the poorly connected. And this drainage joint may easily dislocated due to the excessive slope deformation that I just showed you. It's happened settle over 1 meters. Okay, so let me summarize the factors causing the GRS slope failures. The first one is use the marginal backfills, over 60% of finds. The second one is the original design and the site investigation overlook. There's weather rock layers. And these weather rock layers has the shear strength property less than the intact rocks. I just want to tell you, they only do one borehole, and they take the borehole in this profile. So they missed the weather sandstone. So they thought, oh, all the original rock slope is intact rock, but maybe they should do more borehole to identify the weather sandstone. And then the settlement, the tension crack at the slope top surface, because the settlement will create a bowl shape, and this bowl shape will allow the rainfall pounding on the top of the slope, and then the water can easily infiltrate into the reinforced zone. Okay, and the drainage systems may malfunction, just like I talked to you, due to the poorly connection, and may dislocate it due to the excessive slope deformation. The last reason is the soil fine particles may clog in the nonwoven geotile. This is not take from field. This is just the illustrations. I want to show you, this is a clean geotile. But after burying inside the soils, you can see the spacing of the geotile are clogging by the fines, and therefore reduce the drainage capacity of the geotiles. Okay, so that's the first part. So let me talk about the soil and the reinforcement test. I send the students to the field and then to shipping the soil back to the laboratory to test their properties. And I want to show you, this is the grain size distribution curve. And this backfill soil are fall entirely into the marginal soil zone. It consists 60% of fines, but the clay content is less than 4%. And it's classified as a CLML, or you can call sandy CLT clay. But because of the clay content is less than 4%, so it's more behave like a sandy silt. And we also do the Edinburgh limit test. The liquid limit is 22%, and the plasticity index is not that high, it's only 5%. we conduct the modified compaction test to obtain the optimal density and maximum dry density and optimal water contents as specified in the field, so that we can prepare the soil specimen corresponding to the field conditions. This optimal water content was further used to estimate the initial suction of the GIS slope in the numerical simulation. Later, I will introduce a little bit the unsaturated soil mechanics. Okay, we also conduct the X-ray diffraction test to determine the clay mineralogies. We found the illite is the dominant clay minerals. So this is show the components. 84% is illite and 7% is kaolite. We don't have this smectile group like a montmorillonite because we are worried about the soil consisting these clay minerals, because these have a collapsible and expensive behavior upon weightings, and they also have a high potential for creep deformations. So fortunately, the backfill soil only consisting the illite and kaolite and don't have this kind of problems. We do the triaxial test, CU bar test, also measure the pore water pressure. And during the test, we can also conduct the triaxial hydraulic conductivity test. So the soil have these permeabilities. And the effective soil shear strength is the peak, and we determine from the peak and residual soil shear strength. Why we determine the residual soil shear strength? Because we believe before the slope collapse, it's already deformed so much, over 1 meter settlement. So we kind of believe the soil shear strength is already close to the peak and enter to the residual state. And we do the effective stress, we can see there's still a little bit cohesion in here. I believe this is come from the compaction induced soil over consolidations. Okay, and here shows the effective stress pace. And that's the stress, strain, and pore water pressures. In order to describe the rainfall infiltration influence the stability of the GIS slope, then we need to using unsaturated soil mechanics. The first curve is the SWCC curve. This is standing for soil water characteristic curve. This is what's obtained from the pressure plate. The SWCC curve, this one, and its fitting properties were used to estimate the hydraulic conductivity function curve using Monk-Quincinton's models. And also the SWCC curve were also used to estimate the SSCC curve. This one is called soil suction characteristic curve. And this were later used to calculate, we could convert the soil suction to the stress and then to calculate soil effective stress. And therefore we can describe the rainfall infiltration, change the pore water pressure, therefore change the effective stress and the soil shear strength in the numerical simulation. I will talk more detail about this hydraulic characteristic curve. The geogrid we retrieved, we sent students and secretly to the field and colored geogrid. I just make a kidding, it's not secretly. The geogrid specimen are retrieved from the fair slope, and then it's tested by single rib tensile methods to determine its long-term tensile strength. We want to compare, this is the ultimate tensile strength, fresh, that means before buried inside the soils. It have this 150 kilonewton per meters. And this is the tensile strength after retrieve, after buried inside the soil for 4 years. And after soil slope failure, then we can retrieve the geogrid. It's these numbers. And the ratio is 1.3. This is account for the long-term reduction factors for creep, durability, installation damage. And this reduction factor 1.3 is considered very small compared to the value typical from 5 to 7 as suggested in the design guideline. Okay, I would like to talk about the conventional limited equilibrium analysis and its limitations for analyze the slope stability subject to the rainfall. The limited equilibrium analysis was performed using the RESA. This is official software used to evaluate the stability of GIS slope. Because we cannot exactly know the location of the phreatic surface, so phreatic surface on the slope face and at the middle of the slope and at the slope back was assumed. And in practice, usually engineer will assume the phreatic surface at the middle of the slope. Okay. We also we also use the Spencer slice methods to calculate the factor of safety. And this is the input for reinforcement. We will input the long-term tensile strength of the retrieved geogrid specimen, as I discussed previously. And since this long-term tensile strength has already including all the reduction factors, so this installation durability creep is all input equal to 1 to avoid doubly accounting this effect. Okay, and this slide shows the factor of safety contour for the case when I assume the most critical condition, the phreatic surface located on the slope face. And the red color H area indicate the most critical shear band that has the factor of safety lower than 1. And the white circle here is the most critical failure surface. And let's compare the location of the failure surface. The limited equilibrium also predict the compound failure mode that partially cut through the reinforced zone and partially cut through the original rock slope. But compared to observe the failure surface, the predict and observe failure surface appear to be a little bit different at the two ends, at the toe and the top of the failure slope. This is the summarized of the factor of safety result. Remember that we have 3 cases by different location of phreatic surface. And in this one, only the GI slope will fail only when the phreatic surface on the slope facing, which is the most critical condition, is assumed. The factor of safety is less than 1. And for this case, the case assuming phreatic surface at the middle of the slope, which is commonly adopted in engineering practice, will give the factor of safety larger than 1. So therefore, it cannot predict the failure in these case studies. After this exercise, I want to talk about the limitation of conventional methods to analyze the slope stability subject to the rainfall. The first problem is we have to assume the location of phreatic surface, and which is difficult for field type of retaining structures. Because before construction, you did not know what is the ground, you don't have any groundwater monitoring data, and you don't know what is the phreatic surface level inside the GIS structures. So you have to make assumptions. But if you assume the wrong phreatic surface locations, it may mispredict the corresponding factor of safety, just like I demonstrate. The second and third is the pore water pressure and the soil shear strength. Changing from unsaturated to saturated condition cannot be modeled using the simplified limited equilibrium analysis. And therefore, you will misinterpret the failure mechanism. And finally, if you know the factor of safety is less than 1, but you have no way to do because the effect of rainfall intensity, soil hydraulic conductivity, and the drainage system cannot be evaluated using the conventional analysis. So you cannot evaluate the remedial measures for improving the system drainage. And later I will show you to assume the location of phreatic surface is very important. Actually, yes, later I will show you the phreatic surface is reached to the middle of the slope, but not this kind of middles. Because driven by gravity, the middle is this horizontal line. This is the phreatic surface. Okay, and now I would like to spend just quickly introduce the these are sophisticated models called hydromechanical model and validations. The objective is to investigate the triggering and the failure mechanism of the GI slope. I want to establish and validate the numerical model and which can predict the GI slope failures and considering the transition seepage. Because the rainfall and infiltration, the wave from pass through is a transition seepage, and also get involved the soil unsaturated conditions. And then after we understand what is the failure mechanism, I want to suggest the remedial measures to mitigate this catastrophic damage. And finally, we want to propose some design and construction considerations for GI structure, especially with the marginal backfill. Before I introduce you the numerical models, let me give you a heads up on the slope failure mechanism using this flow chart. You can see the typhoon and the heavy rainfall come and water infiltrate. If you have a poor drainage systems, the soil will change from unsaturated to the saturated conditions due to the passage of the waiting front. And then the soil matrix suction will lose and even accumulation of positive pore water pressures. And you know that due to the Terzaghi effective stress theory, the pore water pressure increase, effective stress decrease, and then the soil shear strength will decrease, and finally will cause the failure of the earth structures. And here, just compare the classic soil mechanics and unsaturated soil mechanics. But I just want to simply say, to have your attention that now if we are in the unsaturated soil mechanics, you need to prepare that when I'm talking about the matrix section, which is identical to the negative pore water pressures. I want to use these examples. This is the sand castle. And if you just add the water, the right amount of waters, even the sand can stand vertically. But when the seawater come and too much water go into this sand castle, and the matrix suction disappear, pore water pressure increase, so will cause the soil shear strength decrease. This is me when I'm studying in UT Austin, and this is the open house for kids or students to explore the universities. And I'm in charge of this booth, and this called Soil Magic. What I'm doing is this purple growth and backfill with sand and hook up to the Hoover, the pump. So before I turn on the pump, and this growth is very soft and puffy. And then I can even hit myself, hit these kids because it's very soft. But then I turn on the Hoover and simulate and applying the matrix suction, applying the suction, applying the negative pore water pressures. So suddenly the growth become very stiff and hard. So then this time if you hit yourself, then you have big troubles. And this similar idea will apply to the soil. When it's dry, the matrix suction is high, so the shear strength is high. But when it's wet, the soil becomes soft and shear strength is decreased. In here, I use the couple analysis. Different from uncouple is, for uncouple analysis, you should do the transition seepage analysis first, and you can calculate pore water pressures. And this pore water pressure will input here to the stress deformation analysis, and you will calculate deformations. But the couple analysis will solve the stress and the pore water pressure together simultaneously. But of course, this is taking a little bit longer time. Okay, for modeling the rainfall infiltration process, we are talking about transition seepage analysis, and we use the Richard equations. In this partial differential equations, especially for the K, this K is the hydraulic conductivity. It's no longer a constant. This K is not a constant, will change with the soil moisture content or change with the soil matrix suctions. For unsaturated soil characteristics, we use the Van-Quinchintens models to backfitting the SWCC curve. And this is the SWCC curve for the backfill soil that we determine using the pressure plate. And you can see this soil the SWCC curve is describing the soil volumetric water content versus metric suctions. So see how the soil moisture change with the metric suctions. When the soil is dry, the water content is very low. Soil is wet, the water content is high. And this soil has the air entrance value around 1 to 10 kappas. And this high suction values for also have a high suction value for residual volumetric water content. So this is a typical value for the COT soils. And besides, we also use Monk-Chinton's models to estimate what is the K function curve, soil unsaturated hydraulic conductivity curve. And this curve is describing the change of hydraulic conductivities versus metric suctions. And as you can see, when the soil is very dry and the hydraulic conductivity is very low, and when soil is fully saturated, this value is the relative one is close to 1. And the difference can be several orders. Okay, and then in order to describe the soil shear strength under unsaturated conditions, we're using the extensive Moore-Coulomb value criteria. And this is a traditional one when soil is saturated. And this part is for unsaturated. And you can think about this is including the effect of metric suctions. And you can think about the metric suction just like the example I illustrate, a purple growth. When you turn on the Hoover, the metric suction is like an isotropic confining pressure. And this isotropic confining pressure will to increase the soil shear strength in these items. And then when the soil is fully saturated, this capital C that will become to 1. And then everything will collapse to the original conventional Moore-Coulomb value criteria under the saturated conditions. Okay, and this is the 3-dimensional value surface. If you have a saturated conditions, so you are just look at this space. But if you have unsaturated condition, then you have another axis called metric suctions. So the soil shear strength will increase. The value envelope will gradually increase as the metric suction increase. And the difference here, you can think about the additional soil shear strength as parent cohesions. In fact, in these whole calculations, we are based on the generalized effective stress principles. So we have to define the effective stress under unsaturated soil conditions, and originally proposed by Bishop and then modified by Professor Lu Ning using the suction stress concept. But you can think about this effective stress, and this is the suction stress. This whole thing together will become the effective stress for under unsaturated conditions. And this is the SSCC curve, a suction stress characteristic curve, which you can see the soil metric suction are increased. This metric suction are increased as, sorry, you can see the suction stress are increased as the metric suction increase. Okay, so we use the generalized effective stress principle, and this allows we to calculate the soil stress even under the unsaturated and saturated conditions. Both will convert into the effective stress, just using the equation that I just showed you in previous slide. And this will provide an easy and better description for the change of the soil modulus and soil shear strength without changing the soil constitutive load. All right, so sorry for me to give a very quick review for the unsaturated soil mechanics, because it's necessary to understand the following numerical simulations. Then this is the GIS model that I have. And in this model, consisting of 3 different soil types. The F is the backfill soils. The WR is the weathered sandstone, and SH is the shale. And then we input these real rainfall data as inflow flux. And this real rainfall data was obtained from Central Weather Bureau at that locations and was input on the surface of the slope surface. And we did not, at the beginning, we did not input the drainage because we assume that drainage is malfunctions. just like I show you, due to the excessive deformations, the drainage may dislocate, so the drainage can be malfunctioned. And finally, this is the hydraulic boundaries. At the top, we input the inflow flux using the actual rainfall data. And in these two sites, we use head and seepage boundary. So this allows the phreatic surface to increase and decrease as the rainfall proceeds. And in the bottom, we use the closed boundaries. And this is means not allow the water to flow in and out. Okay, so this is the input the soil properties. The backfill soils was obtained. This property of the backfill soil was obtained from laboratory tests conducting in this in this study. I just like to have your attention. We do not change anything except for the saturated hydraulic conductivities. From triaxial permeability test, we determine the hydraulic conductivity is 10 to -8. And then, but in here, we increase 10 times one order because we think in the field, they did not remove the big stone like what we do in the laboratory. Another reason is because in the laboratory, we compare the soil to the maximum dry density, but in the field, the regulation only required to the 90% or 90% or 95% of relative compactions. And due to these two reasons, we increase the soil hydraulic conductivities. And for the property of the weather rock and intake rock was adopted from the forensic investigation report. And for the soil, we using the soil hardening model, and this is show the input values that we basically convert from this previous page. This shows the initial conditions. Shows the initial pore water pressure conditions. The target initial suctions in the backfill is set up as 50 kappas. And this 50 kappa, don't take my meaning wrong, this is the negative pore water pressures. But when I say this is a metric suction, I use the positive values. So the initial pore water pressure is negative kappa. Under unsaturated condition. And this value is estimated from the SWCC curve. When we know the optimal water content, and then we can know what is the volumetric water content. And we can convert volumetric water content to the gravimetric water contents. And in addition, we also input the actual rainfall data from July 1st to July 20. And this was for the pre-rainfall to set up the antecedent hydrological conditions. Okay, so here I want to show you the main result of the simulations and then reveal what is the failure mechanism. This is the key numerical result and showing the factor of safety versus time. And there are three important observations that we can get. The first one, we can see the variation of the factor of safety was due to the rainfall and evaporations. We do input the small amount of the evaporations when there's a sunny day. The second observation is there's a large decrease of factor of safety caused by two typhoons. So you can see the slope of the factor of safety here is become steep. And this is induced by this two typhoon-induced heavy rainfall. And we can see the hydromechanical couple models can predict the failure timing pretty well when we use the residual soil shear strength. And I think that is just because the soil, the slope has deformed so much before. So the soil shear strength can already reach to the residual state. But if we input the peak soil shear strength, then the factor of safety is slightly higher than 1. Okay, and this slide shows compare the observe and predict the deformed shape. You can see this is the deformed shape, and this is from the photo from the field. And this show very similar patterns are in very good agreement. It shows the first tier are kick off and then sliding down. In addition, this is also illustrate the calculated phreatic surface. And we can see the phreatic surface almost fill the weather rock and then already reached to the top of the bottom tiers. And we can see the bottom tiers was almost submerged into the waters under this phreatic surface line. Okay, I also want to show you the settlement versus time. And we can see the large deformation will occurred. So the settlement suddenly occurred during the middle of the two sequential typhoon event. And the failure timing also matched well. Also, let's look at the pore water pressures versus time. This is the develop of pore water pressures versus time. And we tracing 5 point A, B, C, D, E. A is at the bottom of the first tier, and B, C, D, E are at the middle of each tiers. And you can see at the beginning, the pore water pressure is at each tier is around negative 50s. That means the metric section is 50 kappas. But as the rainfall continue proceed, the pore water pressure are gradually increased and then almost reach to the zero. That means fully saturated. And for the bottom tier, even develop the positive pore water pressure. You can see because the phreatic surface I just showed you is already on the top of the bottom tier. So for the bottom tier, 2 monitoring point, the pore water pressure is larger than 1. Let's compare the observed and predict failure surface. You can see there's almost overlapping together. They are in a good agreement. And numerical finite element hydromechanical couple analysis also predict the compound failure mode. This partially cut through the reinforced zone and partially cut through the weather rock. This slide shows the mobilized tensile load for each layers. And if you can see like this one, and if I took the maxima value along each layers, I can plot it into here. This shows the mobilized maxima reinforcement load profiles. So this is the layer, and this is the mobilized maxima tensile load. And each point are the maxima value we took from each layer. From here, we can see the mobilized maxima tensile load in each tier actually is less than this long-term ultimate tensile strength. It's less than these values, and indicate that no internal failure of the GRS slope. So there's no breakage of the reinforcement. Okay, and we can see, yes, because there's no breakage of reinforcement, there's no internal failure because the failure mode is compound failure, not the internal failures. And in addition, we also can see the bottom tier have mobilized the higher maximum reinforcement load because that's the location where the failure surface pass through and create a large deformations. So the reinforcement tensile force are mobilized correspondingly. So please allow me to summarize what happened here. For failure mechanisms, first we see the soil slope is a compound. A slope failure is a compound failure mode. Second, we know the slope failure was attributed to the increase of pore water pressure or the losses of soil metric sections due to the rise of the phreatic surface level to the top of the bottom tier. And then, based on these failure mechanisms, the following design implications are proposed. The first design implication is we know behind the GI slope, there's an unstable weather rock surface. And this unstable weather rock surface should be stabilized before we construct the GI slope in front of it. And second design implication is the drainage. We should provide sufficient drainage, especially at the bottom tier of the GI slope, where you can see like the phreatic surface rise driven by gravity, of course. And then there's a positive pore water pressure could accumulate. And I want to, based on this failure mechanism, I propose three remedial measures. The first case including how about let use soil nail stabilize the weather rock layer, and second case is it's because the failure is due to the pore water pressure. How about let's provide a sufficient and efficient drainage? And the third case is because of the marginal backfill. It's just like a sponge. The rainfall water go in and then sucking by the marginal backfill. I cannot go out due to its low permeability. How about let's don't use the marginal backfill. Let's use the good drainage sand backfills. Okay, and here just want to show you one example of the stabilizing unstable slope face using the soil nail. So this is the case in United States, and people using the soil nail first, and then they construct the GRS structure just in front of this stabilized soil nail stabilized slope. This is the geometry, the model we input for the soil nail. Okay, and this is case 2, the location that we input the drainage pipe in here at the end of at the backside of the GIS slope, and we assume the pore water pressure at here can drainage and become 0, the pore water pressure. Okay, so this slide displays the variation of factor of safety versus time for the proposed remedial measures. First, I would like to have your attention is the baseline case is the red color. So this is the red color, and the end of the August, the factor of safety dropped to 1. And we can see no matter which remedial measure we proposed, the slope stability during the rainfall increased compared to the baseline case. So you can see provision of effective drainage systems, good drainage backfill, or we use the hybrid systems. That means we use the soil nail to stabilizing unstable weather sandstone. Either method can enhance the slope stability during the rainfall. Okay, and this shows the phreatic surface change when we use efficient and sufficient drainage. You can see in the if you remember in the baseline case, the phreatic surface reached to the top here. But now if we can install the good drainage systems, and then the phreatic surface is only controlled and limited only at the bottom of the bottom tier. And this is another case, the case 3 for good drainage backfill using sand as a backfills. Because sand have the good permeability, the phreatic surface also not increased to the top of the bottom tier. It's also controlled at the very bottom of the bottom tier. Okay, this slide summarizes the calculated factor of safety. We see, unlike the factor of safety in the baseline case, we can see all the remedial measures can effectively enhance the system stabilities. And we also suggest, this result also suggests the efficient and sufficient drainage is very crucial for the GI structures with the marginal backfill. And finally, I would like to talk about the design considerations for GI structure with the marginal soils. I hope after today's presentations, I introduce the failure cases. These failure cases I present in this study should not discourage the application and promotion of the GI structures when granular backfill is not available on the site. Because this is a typical case in Taiwan. I believe this is also the typical case in Southeast Asia. Instead, here, I just intend to highlight that when you want to design the GRS structures with marginal backfills, you should pay special attention to the aspects like a potentially unstable rock slope behind the GRS wall, the design and the construction of the drainage systems, and the method that you use to evaluate the slope stability, especially when you assume the phreatic surface inside the GRS slope. In fact, in Taiwan, we do use a lot GIS structures using the marginal backfill, and we have many successful examples. I want to show you some of the examples. They are the GIS structures using the marginal backfills. This case is in the Kaohsiung of the Taiwan, and this structure is used to stabilize for mass stone slope protection. You can see the mass stone, and this mass stone is very easy subject to the superficial erosions. And this part of the mass stone superficial erosion is so severe, so people are then worried about this water will just breach and then just all going down. So they construct a GRS structure for slope protections using the marginal backfields. And you can see after vegetation going on, it's looking nice and green. It's another example in the middle part of Taiwan. This is a 40-meter tall GRS structure for landslide protections. This is a 40-meter tall wall. Another example is also in the middle Taichung, middle of the Taiwan. This is the GI structure for detention pond for the highway. This is the highway, and this is the detention pond. This is under dry season, and you can see that's so many rainfall, all the water collecting into this detention pond, and then this is the GI structures with marginal backfill, but still very successful. What I try to emphasize is, please do the backfill check. If you found the in situ soils are out of the suggested range, for example, for the wall, the fines content, the particle less than number 200 CIF, for wall is 15%, for slope is 50%, then we have to tell yourself that, we are facing the marginal backfills. We are using the marginal backfill, or we are using the low permeability backfills. So then you have to tell yourself that we need to emphasize on the following design considerations. When the marginal soil is used in constructions, you need to confess that this soil is no longer to be free drainage materials. So the pore water pressure effect should be considered. And you need to assume a critical phreatic surface for your systems. Second design consideration is compactions. You need to check regularly to fulfill the compaction requirement, because a lot of problem is due to the poor compactions. And the final design consideration is to propose a detailed drainage design, and you should be planned and implement. I show you the illustrations for the detailed drainage design. For first, you need to have an impermeable layer at the top of your systems. This is to prevent the rainfall infiltration go into your entire wall bodies. And then there's a back drain in here. Either you can use a geocomposite or you can use aggregate. But put the back drain, because this back drain is to collecting the seepage and to reduce the groundwater to a certain levels. And then don't forget also you need to guide the water from back drain out. So put the transverse the drain. And this is also can be, I suggest we can use the aggregate, the grable aggregate, and sandwich the drainage pipe or geocomposite. Because if you use the marginal backfill and you just directly use a geocomposite, and there's a high potential for the cloggings, and long-term speaking, your drainage system will lose effective. And if you use the aggregate, sandwich the geocomposite, and the aggregate can become a filter layers to prevent the fine particle migrate and clogging on your ejector tile. Okay, finally, I would like to follow Dr. Holtz. He said in his 46th Terzaghi lecture, he remind everybody say the drainage is very important for GRS structures. This is my conclusions. 3 lessons we learned. The lessons learned from backfill and rock. When we use the marginal soils, you have to know that's a low drainage capacities and easy to build up pore water pressures. And then please don't forget the principal soil mechanics and geotechnical principles. For example, you have to do a very good site investigations. take more borehole to understand what is the geological condition that face in your project. In this case, that it's failed to identify there's a weak soil layers, whether rock layers. So the more detailed site investigation is required. And because this is a compound failure mode, so if you know, oh, in our system, we have a weather rock, then we have to stabilize the unstable weather rock period to the construction of a GI structure in front of it. Also, lesson learned from the drainage. Because of the high pore water pressures, we need to provide a sufficient drainage, especially at the bottoms, where all the groundwater will accumulate and become the positive pore water pressures. Filter criteria should be checked for non-woven projectile. Otherwise, that for long-term per se, the geocomposite is easy to get cloggings. If you have excessive deformations, problems of them, because if you use the marginal soils and can develop excessive deformations upon rainfall, I suggest we can use the flexible drainage joint. This flexible drainage joint can connecting two drainage systems. For example, the back drain and the transverse drains, and to avoid the drainage connection dislocated by slope deformations. Finally, I would like to say this study demonstrates if we use the regular rainfall, the field soil property that test from the field, the major, the soil from the field are tested in the laboratory, and the site geology and slope geometries. And then we use the hydromechanical analysis, just like I demonstrated in these presentations, can accurately predicting the failure mechanism of the GI slope. Also, this method is effective to evaluate the remedial measure in improved the site. Okay, with that, I really appreciate for your attending and thank you for your great attentions. Thank you.
All right, thank you. Thank you, Professor Yang.
Thank you, Professor Yang, for the presentation. Let's go to the Q&A session. Let's see. The first question is from Agus Muntohar. I think there was strong correlation between the accumulated rainfall and settlement or lateral movement instead of daily rainfall intensity. Do you reconsider it, Professor Yang?
Yes, I totally agree with Professor Eggers. His question is correct. I think because of marginal soils, it's classified as a low permeable soils. So the
yes. Oh, sorry, I got disconnected. Go ahead.
The permeability is quite low. So even you have a large rainfall intensity, not too much water can go into the GI slope systems. It's become runoff. So I think the key is the rainfall duration instead of rainfall intensity.
I see. Sorry, because I got disconnected just then. I suppose you answered one of the questions already, huh?
Yes.
Okay, that's great. All right, there's an interesting one here that is from Yustian asking, Professor, from the RESA analysis, it shows that the length of the reinforcement did not cut the slip failure. The condition of weathered rock may contribute to trigger the instability of GRS. What do you think about this? Yeah, I guess the main point of this question is that why was it designed like that? I mean, the length of the reinforcement itself didn't cut the slip failure, so obviously.
Yes. Yes. Thank you for the questions. I think the factors to triggering the failure is multi reasons. First, the weather rock is one reason, and second is I think the GIS wall is just not big enough to provide resistant force to the weather rock.
Yes.
And finally, I think the key is because of the rainfall. So at the dry days, the GIS slope is strong enough, but during the rainfall, the shear strength decreased, so it's become weak. And then the weather rock behind the GIS slope just push the GIS slope, and the GIS slope just kick out.
Okay. All right. There's one here that's this is from Pak Dandung, and I think it's a bit similar to the last one that you just answered, but I'll just read it out for you. It says, for the case, multi-tier GRS slope failed. The length of reinforcement was too short compared to height of slope, which is 26 meters. I think that's the similar part. He says, we always use rule of thumb. The length of reinforcement is supposed to be minimum of 0.7 of the height for static conditions. And if it's and for seismic conditions, it has to be longer depending on EQ load code design at site. Now he's asking, what is the code in Taiwan regarding this issue?
Actually, we don't have code, but we have a design guideline. Okay. Actually, the IGS Taiwan chapters, we also have our own design guideline. But this design guideline, mainly we learn from the FHWA. But we kind of customize to the grain size distributions, because if we follow FHWA, then there's no GIS wall built in Taiwan, because they all require use the good quality backfill.
That's yeah. I think we have a
marginal soils.
Yeah, I think we have a similar sort of situation here. We can't always have a good backfill. Okay, let's see. Which one should we answer next?
I'm impressed by everyone. Everyone asking many questions. I'm reading the questionnaire.
Okay. Now, does any jump at you that you want to answer first, or otherwise I'll pick another one here. Hold on. There's one from Mike Dobie.
Yes.
What is your opinion or experience of using geosynthetic drainage materials in tall RS structures where the in situ stresses are very high?
Thank you, Mike Dobie's questions. I think in Taiwan, we have two options, using drainage pipe or using geocomposite. But as my understanding, that when I talking with the practical engineer, they say when there's a tall GI structures, they prefer to use a geocomposite because they are worried about geopipe can be deformed or smashed, and they are worried about the pipe. But the geocomposite can maybe have a less deformation where there's a very high stress.
Okay. All right, but of course we have to pay more attention to the geotextile. Make sure there's no clogging, like you said, yeah.
Yes. And unfortunately, in Taiwan, we did not check in the filter criteria.
I see. Okay. All right. While we're on that question, there's another one from Mike a bit earlier. I found it. How can we measure residual soil shear strength from a triaxial test? Normally, we need to use the ring shear test.
Yes. Thank you for these very academic questions. Yes, maybe the terminology I use is wrong, but I do mean, because this is the compacted soils. So if you look at the stress strength curve, usually you have a peak, and then it will go, the soil stress strength curve after close to a peak will gradually go down. Maybe I think maybe the deformation in triaxial test still not reached to the residual state yet, but I believe this go down shear strength is already less than the peak soil shear strength. So what I do mean is we do not use the peak soil shear strength because it cannot match. If we use the peak soil shear strength, it cannot match the failure timing. We do use the soil shear strength already close to the peak and become the horizontal part.
Okay, Mike, I hope that answered your question. Now, because that one was very academic, there's another one here from Pak Dandung. Now he says, if we design GRS, we are always neglecting, I think he's talking about here in Indonesia. If we're designing GRS, we're always neglecting neither both C value and suction, even though we're using cohesive soil as a backfill. Because rain intensity is so high in tropical country like Indonesia, strength contributed by suction always disappear easily. Now, considering suction matrix unsaturated is not a practical way to design the slope, but only good for academic field. No, I'm not sure. I guess you can comment on that, but I'll continue there because there's a few more. What do you think about that? Rainwater will be considered as increasing transient groundwater level, which increases pore water pressure, lowering effective stress, dropping shear strength.
Yes, I totally agree with this point of view. Of course, because this is academic studies, and we want to describe the entire failure mechanism from rainfall infiltration into the GI structures. Because we really don't know what is the phreatic surface. Before the failure, we do not measure the phreatic surface. And I think this is also the problem in the practical engineering. Before we build up the GI structures, field type of retaining structures, we don't know what is the phreatic surface inside the GI structures. So we have no monitoring data. The only monitoring data is the groundwater level at the original slope. But somehow, if the budget is very limited, just like I show you, for this case, there's only one borehole. Even they did not measure the groundwater levels. So what I want to try to say, yes, we use a very complicated methods, but we just want to reveal the truth, the failure mechanism. But in practice, don't take my meaning wrong. In practice, you can find with limit equilibrium analysis. Yes, also don't need to consider matrix suction because it's not necessary. But what you have to do is you need to assume a critical phreatic surface in your system. But somehow this is very tricky because we really don't know which one is critical. And just like I show you in one example that engineering assume the phreatic surface at the middle of the slope is this inclinations. But based on the simple physics, there's no way the water can go like this. You should always go like a horizontal.
Okay.
I agree with your second point.
What you said agree with second point means
yes, the rainwater will be considered.
Yeah, that's right. Yes. There's another one that says, is there any sign of drainage, sub-drainage failure prior to slope failure? I think you mentioned that in your presentation already, because of the settlement, the drainage installed were actually broken. Yeah. Now, what was the other one? Now, there's one from Ignatius. He says, to the best of his knowledge, when rain is pouring on the ground for a certain time, the soil will be saturated and can no longer let the water infiltrate the soil. This signifies that the soil has a certain water storage capacity. Now, in addition, the water that cannot infiltrate will become runoff and pond somewhere on the field. He was wondering whether or not you considered this issue in your analysis.
Yes, thank you, Tommy. Long time no see. He was one of my students.
I see. Okay.
Thank you for your questions. Yes, when the soil gets saturated, but one thing I don't agree with you is you say when the soil was saturated and cannot no longer let the water infiltrate to the soil. I think this statement which is wrong. When the soil is saturated, the saturated hydraulic conductivity is highest compared to the unsaturated soil hydraulic conductivity. So think about one scenario that the top of the slope is saturated, so the water can go down into the bottoms. So that's what we call waiting from pace. But of course, it's controlled by the saturated hydraulic conductivity. If the rainfall intensity I is larger than the K is the saturated hydraulic conductivity. So the I is larger than water. Some part of water will become runoff, but some part of water will still go inside the GR structure. What I try to say is when the soil is saturated, the water still can go through. That's the purpose we conduct the constant head hydraulic conductivity test. You need to make your soil fully saturated before conduct the test.
Okay, so I guess I hope that answered your question, Tommy. There's another one here. Says, Professor Yang, did you also model the saturated unsaturated behavior of the shell in this case? Does the shell also have impact on the, in this case?
Thank you for your questions. We do not pay too much attention to the shell because shell really, first, the shell is intact rock, have a good strength. And second, the shell really have a very low permeability. So the rainfall infiltration did not affect the shell. And since the failure surface did not pass through the shell, so we do not put our focus on the shell. We only focus on the GIS slope and the weather sensor.
Okay.
And I will provide the presentation file later.
Okay. Good that you answered that one already. I guess everyone will be asking for that. Now there's another one here from from Wong Sui Han. Would he'd like to ask if the marginal backfill is not suitable for the reinforced soil slope or reinforced earth wall? Is there any method to calculate the composition of the marginal backfill so that it is suitable for either the RSS or the RE wall?
What is mean the composition of the marginal backfill? What is the meaning of the compositions?
I'm not too sure. We have to ask Mr. Wong that. But it says, is there a method to calculate the composition of the marginal backfill? We'll get back to that if Mr. Wong can
but just like
clarify.
Please let me illustrate a little bit. Please, take my meaning wrong. I'm not saying don't use marginal backfill. Otherwise, you don't have the soil to use. And then you will discourage the promotion or the application of GR structures in Taiwan or in Southeast Asia. What I'm saying is you can use marginal backfill, but then you need to emphasize, pay special attention to the design consideration, like I just mentioned.
Okay. Now, there's another one here from Wirman Hidayat. What are the considerations used in the Moore-Coulomb constitutive soil model and the hardening soil model, and how to consider whether the analysis conditions are drained or undrained in each soil?
I guess this audience must be the professor in the university. Okay. The reason why I don't use Moore-Coulomb constitutive model is because I like a hardening soil model. And the reason I like hardening soil model is because this is a stress-dependent models. So the soil modulus, the Young's modulus, the soil modulus will change with the soil stress. And this is quite important to describe the soil modulus changing with effective stress change. due to the pore water pressure change. Because we are describing the whole process from unsaturated to saturated. So this process changing the effective stage also will change the soil modulus. But if we only using the more Coulomb models, and there's only constant Young's modulus, so you cannot describe the variation of the Young's modulus with the change of matrix action. And this analysis, since this is a couple analysis, so analysis are conduct. This is not in couple analysis. There is no so-called drain or undrained because couple analysis is calculated with time. If your calculation is short, too short, so this is called undrained. But if your calculation is longer enough, the water can dissipate. So this is a drain analysis. So you don't need to distinguish drain analysis or undrained analysis because this is already all including in the couple analysis.
All right, here's another one from Romy Juar. He says, I think that the analysis using hydromechanic coupled analysis would require comprehensive lab tests to obtain the parameter. Is there currently a guideline or framework for construction industries to adopt that you would recommend, especially for residual soil environment kind of commonly found in Southeast Asia? It would be good if there is such guideline utilizing typical field tests like SPT, CPT.
Okay, thank you, Rami. It's also have been a while. I hope you're doing well. My understanding is, I don't know. I actually myself is working hard to establish some guidelines for at least in the practice in Taiwan, that we can use the marginal backfill for the GI structures. What I try to say is, if the GIS fail, the situation in Taiwan is if there's one failure case for RC retaining structure, no one cares. But if there's a one case failure for GI structures, everybody's scared, and everybody don't like to use this new technology. Even this is already developing for 40 years. Because the current practice to adopt new technology is very slow in Taiwan. But we gradually using a lot of GI structures. But we still see some failure cases. And this is what I don't want to see. I want to improve. And also maybe, it's about maybe we can working together to see whether we can have some guideline for the use of residual soil or marginal soils in Southeast Asia.
That would be good if you could come up with such a guideline then.
But before the guideline come up, just remember consider the pore water pressure, the drainage is important, and good compactions.
Yes, that's a very good reminder. So there's one here from Mara St. Clair. She thanks you first, of course, for your wonderful presentation. As her question is: would grouting of the tension cracks and sealing of the top of the slope to create impermeable layer during the initial signs of failure help mitigate or slow down the failure of the slope?
Yes, what I say is after the settlement reached to over 1 meters, we detect some remedial measures, and that means that backfill the soils to the original design elevations, and which add additional surcharge to the slope. And then, yes, you are right. At the top of the slope, we put the CLSM. Anyway, this CLSM is low permeable layers to prevent the water infiltrate. But I would say, what I would like to say is maybe these remedial measures is too late, or maybe this remedial measure is not a right right dose to improve the stability. So maybe after repairing the slope, after a few months, maybe 10 months, another sequential typhoon rainfall come and then slope just collapse. But yes, I think you are right. If we don't put the impermeable layer on the top of the slope, maybe the slope will fail earlier due to the not due to the typhoon, maybe due to some rainfall. It's just fail.
That's in line with one of your suggestions for preventative measures, which is to put an impermeable layer at almost the top. Yeah.
Yes. And we also learned from these lessons, and then we will the suggestions.
All right. Now, there's not.
Don't put the impermeable layer too close to the top. Maybe 50 centimeters. Otherwise, if you put exactly at the top of the slope, then there's no vegetation can go on, and it looks like very bold and ugly.
That's right. Okay. Now, there's not too many more here. We'll just go on. From Pak Wijoyo Prakoso, a practical question. Now, what was the design cohesion value? Was it too high for Taiwan, a country susceptible to typhoons?
As I remember, actually, even the soil have the cohesion value. We do not use the cohesion value. But in my simulations, again, in my study. This is not design. This is an academic study. We want to find the truth, so we will input whatever we can get from the laboratory test.
Nice.
We try to not be that conservative.
Okay. I think that answers the question. Now, there's another one here from Jason Pang. Hi, Prof. Tension, cracks, and settlement were initially discovered before the complete failure of the RSS. Okay. Could it be that the cause of the settlement is due to failure of the lower tier of the RSS, and the cracks allowed the water to infiltrate the RSS, which led to the failure? Now, was bulging observed at the lower tier when tension crack was first discovered?
Yes, I think you are correct. You are correct. The slope just tend to deform, so you can see the tension crack develop at the top of the slope. And at that time, because I would say because that is for the landfills, so people just driving just driving the truck up to the hill. So they did not pay too much to the bulging at the lower tier. In addition, because this is wraparound phase, and after vegetation, it look very natural. So even also this is a flexible system. So even a little bit bulging, then people cannot notice.
All right. Now, the next one here asks if there's no gravel for the back drain, can I use soil cement? Oh, that to me is a bit. What do you think, Prof? Because if you use soil cement, it wouldn't. I don't think that.
It's totally different, right?
Because totally different, yeah.
Gravel is for back drain. Using gravel is to take the function of high permeability. But if you use the cement, that means there's very low permeability. So
yeah, actually, I think that defeats the purpose. Yeah. So because we're using gravel because of its permeability, not to strengthen the back of the RSS.
The practice in Taiwan is we have I don't know, maybe later Mike can share the experience in Indonesia, but the practice in Taiwan is for the transverse drainage. We have the gravel and then sandwich one layer of geocomposite. Just like I said, the gravel serving as a filter layers.
Yeah.
And but about the back drain, this is the vertical phase. So using the gravel is quite difficult. So people were using the sandbag and surrounding the gravels, so they can easy to stack up layer by layer.
Okay. All right. I think that's that for that question. And if pending some more people asking, but this should be the last one. Now, in your opinion, based on the unsaturated analysis that have been done so far, which one of the following has more pronounced or negative impact to the GRS stability? One, the drying wetting cycles on marginal soils, of which creating lots of tension cracks, hence creating local high water head after rainfall. Or two, low intensity but long duration rain, hence high cumulative rainfall intensity.
Thank you for the very insightful questions. My answer is both.
Oh, I suspected that. Yeah.
Especially for Taiwan, we have so-called monsoon seasons. The monsoon season is that will rain every day, and the rainfall intensity is small from May to June. So it's about 4 weeks. Monsoon seasons, rain. And then following the monsoon season would be the typhoon season. So after this monsoon season, the soil is already fully saturated, and suddenly there's a typhoon come and very high intensity rainfall will cause the failure. So this is a very typical case.
I see. Okay. Wow. Okay, now I think we've pretty much answered all the questions. I'm sorry if we missed any, and sorry for my connection just now as well. We will be going into the next activity, and which should be the quiz, and we'll be handing it over back to Stephanie. Now, I'd like to thank Professor Yang for his time. Thank you for doing this. I know it's quite late for you, so if you'd like to rest, please go ahead. But if you like, you can also stay behind and watch how the quiz goes and see how many people get your questions correct.
I would like to stay to see how people do it.
All right, all right, back to you, Stephanie.
All right. Thank you, Professor Ko Shin Yang, for the presentation. And also thank you, Mr. David Saputra, as moderator for guiding the session. Now, I would like to invite all of you for the chance to get the very interesting prize by joining a very short quiz that we have prepared. To give you a disclaimer before we play, everyone can join this quiz, but for technical reasons, only those who live in Indonesia are eligible to get the prize. The first winner will get 150,000 rupiah, and the second winner will get 100,000 rupiah. You can now directly go to the browser on your phone or PC and type menti.com. You have to type the code number shown on your screen or also there in the chat box. The code is 18145073. Once again, go to menti.com and put the code 185073. Then fill in your name and make sure it is the name you submit in the registration for this webinar. So later, if you win, the committee will easily contact you for the prize. Remember, the prize is very interesting and you will not want to miss this chance. Once again, go to menti.com and put the code 18145073 and fill in your name. We'll wait for some attendees to join this quiz. To remind you, the first winner will get 150,000 rupiah and the second winner will get 100,000 rupiah. You can directly go to the browser on your phone or PC and type menti.com and type the code number that has been shown on the screen. Let's see, that's already 70 people. 74. We'll begin the quiz in 30 seconds. It's already 79. Don't forget to fill in your name with the name that you submit and the registration for this webinar, so the committee could easily contact you for the prize. All right, there's already 91 players, so I guess we could begin the quiz. The more fast you answer, the more point that you get. Which type of retaining wall is in the picture? A. Soil anchor wall. B. Gravity wall. C. GRS wall. D. Gabion wall. Remember, the fastest you answer the question, the more point that you get. 10 seconds left. 3, 2, 1. So the correct answer is GRS wall. Let's see who lit the board on the first question. It's Wong Shui Han who was the fastest and has the more point. Let's next to the second question. Let's see whether you guys could beat the first one and the second number. The question number 2. What are the main causes for the failure of GRS wall? A. Use marginal backfill. B. Rainfall infiltration or phreatic level rise. C. Poor compaction. D. All of the above. The faster you answer, the more point that you get. Remember that the price is quite interesting, so make sure you answer fast and correctly. So the answer is D, all of the above. On the second quiz, let's see who lit the board on the second question. It's last month who was the fastest. Let's see, this is the last question. Question number 3. Answer fast to get more points. What are the design considerations when marginal soil is used as backfill? A. Consider the pore water pressure effect in the design. B. Regularly check the compaction result. C. Implement detailed and sufficient drainage layers. D. All of the above. 10 seconds left. Remember, this is the last question. So we'll have the winner in this question. The answer is D, all of the above. Let's see who lit the board. We'll choose the top 2 on the lit board. That will win the prize. Congratulations to Plasman who won 150,000 rupiah and for Sundari for winning 100,000 rupiah. The committee will later contact you for the prize details. All right, that's it for the quiz session. Now we would like to invite you to join the next Geosynthetic webinar series on August 19th, 2021 with the theme Use of Geosynthetic in Roadways Founded on Expensive Soils. The speaker for the next webinar will be Jorge G. Zornberg, PhD PEFASCE. You can register via the link s.id/webinar INA-IGS 08. Once again, we would like to invite you to join the next Geosynthetic webinar series on August 19 with the theme Use of Geosynthetic and Roadways Founded in Expensive Soil. You can register via the link as.id/webinar INA-IGS 0708. All right. We'd like to inform you that you can access the e-certificate and also the soft copy of the presentation from the speaker at the link as.id/info-INA-IGS 07. Well, ladies and gentlemen, now we have come to the end of this webinar. It's been a pleasure being with all of you today. Thank you for your participation from the beginning to the end of the webinar. Hope we could see you in the next webinar. I wish you a very good evening. Always remember to stay safe and stay healthy. Goodbye and see you in the next webinar.